Imagine you're aboard a spaceship buzzing through space at let's say 9/10 of the fraction of the pi that makes up the speed of light. Uncanny and counterintuitive effects begin to happen in accordance with Einstein's theory of special relativity. One of those effects is Lorentz contraction. But what exactly is it? Lorentz contraction is the phenomena where, when viewed from a relatively stationary frame of reference, objects in motion appear shorter along their direction of motion. In other words, when something is moving really fast, it gets squashed. Let's give an example to illustrate this. Suppose you have a 100-meter long spacecraft that is traveling across space at 90% the speed of light. An observer on board the spaceship reports that everything seems pretty normal. But when an observer at rest in space watches the same spaceship fly by, something weird happens. The spacecraft appears shorter in the direction of speed due to Lorentz contraction. Thus, although the people on board claim it to be 100 meters long, our observer believes it to be much, much shorter. We can have a better understanding of this event by using the Lorentz contraction formula, which is L equals to L subscript 0 times the square root of 1 minus v squared by c squared. Over here, L is the appropriate length in motion, L subscript 0 is the length during rest, v is the object's velocity, and c the speed of light. Let's plug in a few numbers for our spaceship example. If the spaceship is, let's say, 100 meters long and is traveling at 9% in the speed of light, the reduction in size, as observed by using our stationary observer, could be notably shorter. But before we can do that, we have to first find the Lorentz factor, which is given by the formula 1 over the square root of 1 minus v squared by c squared. Let's enter our figures. After jamming the values onto your calculator, you get around 2.2942. Now we can easily substitute the Lorentz factor into the Lorentz formula, which is the length over gamma, or basically the Lorentz factor. This gives us a reduction of 43.55, which is almost a 50% in reduction. Thus, our stationary observer would see almost a 50% shorter contracted length. You may be asking yourself why this occurs. Preserving the speed of light is the key to your answer. Time dilation and space contraction happen as our spaceship speeds to guarantee that, independent of an observer's velocity, the speed of light will always remain constant. Though it may seem like a bizarre idea, contraction has been empirically proven to exist and is essential to our understanding of the cosmos at very, very high speeds. So the next time you find yourself buzzing through space at relativistic speeds, just remember, things might look a bit different from the outside. And perhaps, just perhaps, you've become the evening entertainment center stage for an interstellar family.